I expanding that tab for morning.
Hello?
Hello, Christopher. Hi, how are you?
Not bad.
Okay, good. So, school holidays already started?
Tomorrow's the last day of
Tomorrow's the
school.
last day.
Yeah.
All right, okay. Okay, good. All right, okay, let's just go into it. So we probably take a break halfway through because we have at 1 hour, 3/4. So probably have a bit of a brief break in between because it's all about resistors mostly probably today.
Oh.
So, okay. And okay, to see my screen?
Yeah.
Okay. All right. Just a sec. Pencil connected. Okay. So last time we basically towards the end stopped about the basic or resulting basic laws when you have either series or parallel circuits based upon Kirchhoff's law. Huh? So that's why they are so important. Once in a while, you may have to deduce why the laws are like that. The ones we apply, these are basically the practical applications of Kirchhoff's law. There are a couple of things to remember, but instead of me telling, maybe Chris, if you could just tell me briefly what are the key draw points from the series and the parallel circuits in order to keep in mind as we need them to calculate later on the various parameters.
In series, the current is the same at any point.
Okay.
And the sum of the EMF is equals to the sum of PD.
Okay. Which means in most of the time that you have one EMF and a split PDF most of the time, but it's completely correct what you say. So there's usually only one EMF in 90% of the cases we are dealing with, but obviously many PDFs. Okay. Yep.
And the resistance of the circuit is the sum of the resistance of the components.
Yes, right. Huh? So that's quite straightforward, seemingly. Huh? Okay. Then what about parallel?
Current is split up into.
Yep.
I think I should say the sum of currents in each loop is equals to the current of from the main
I'm losing you, Chris.
cell.
Yeah, you're right. I just that the network was a bit fuzzy.
Oh,
Can you just say it once more, please?
the sum of the currents of each loop is equal to the current at the main electric cell.
Yeah, exactly right. So we have a, like you said, you can either way say either split or the sum. Absolutely. What happens to the voltage, the PDF?
The sum of PD in each loop equals to the main EMF.
Yep, that's correct, right? So they're all the same. No? So for each stream, for each loop, each line of the circuit, so to speak, in the parallel situation, there's the same PDF across each of the individual ones. Yep. I will come back to that a bit in more detail, why we didn't have the time last time. I want to explain that a bit more, why, actually, okay? And then the resistors.
The resistors in parallel, the resistance of the components in parallel decreases the total resistance. I mean, like,
Okay, yeah, that's an interesting remark. Yeah, that's a good remark from a practical point of view. When you look at the math, how would you express it?
the inverse of the sum of inverse of the resistances. Right.
Yeah, coming close. You just need one. I mean, when you have the inverse of the resistance of the components, what do you have to add there, or put to the front?
In parallel. So,
No, exactly. Yeah, in parallel. Okay. Just the sum, right? I mean, that's what I wanted to say, right? So the behavior of the resistance in a parallel circuit is as such that it is the sum of the inverted resistance is equal to the total inverted resistance, right? So goes just by the fraction of it, actually. So in other words, you just add the fractions are then equal to, of course, makes a lot of sense, right? You add the fractions, so the sum of the fractions is the fraction of the total, so to speak. And it depends on what you got. Sometimes you will not have anything here. You just go here. And of course, in the end, you probably want to know this one. So in the end, you have to invert it in order to get the resistance. And that's what you said at the very beginning. Then actually that diminishes it. So that's an interesting behavior as well. Today, briefly cover that. Okay, so this one was basically why it's like that. So why is it inverted? It's always following Kirchhoff and the basic law of what is the relationship between voltage, current, and resistance. That is always one part of any of the equations plus the basic Kirchhoff's law. And when we apply them, then we get the result. Now, the one thing which I haven't covered last time is briefly why it's because it's a bit odd why we come into the invert, right? It's yes, from the math kind of yep, of course that follows from how it works, but the starting point is a bit different, and the reason why it's like that, of course, we have to start, and I want to draw that circuit briefly, very basic one, and then the moment you see it, because we look at individual circuits like that. I mean, we had that before, right? So just do it once more. And here we go. The nodes, and we say we have a current in and we have a current out. And of course, we then have a split. So one goes up, the other one goes down. Of course, and it flows in this direction and flows in that direction. And we have a resistance 1 and a resistance 2. 2, sorry. So when you now look at the voltage, now the key point is to say, okay, I make that in green. no, in red maybe. Across that one, we have the voltage. So that is so across the whole circuit from A to B, normal stuff, right? Nothing special from here to here. We have that one. Of course, then it's a special case that we split it. That's why we then have the special situation in the end. But across the circuit, there's one voltage, of course. That's important to keep in mind. Now, when we apply Kirchhoff, of course, we can say the standard, that's normal, because that has to, we did that last time actually, that one. Of course, it's the sum, right? So if they come together here, then they must be identical to this one, and vice versa. This one, when it splits, the outgoings, they can only be equal to the sum of the incoming. That's standard Kirchhoff. Now, when you apply now the second of Kirchhoffs to the loop, basically that's one loop, right? That's one loop here. We have the following situation where we say, okay, the sum of the PDFs is equal to the EMF. Now, when you look at it, what would you expect the EMF is in that loop? Just from the simple drawing, and don't think too far. Take it at face value, so to speak.
We use the total current, total current times the resultant resistance.
Yep, but that's correct. And what will the result be in that specific circuit here? What will the result be for the EMF? What value will it have? Or in other words, do you see an EMF in this circuit?
There should be.
Okay, good point. Yeah, there is none, right? Exactly. It doesn't have to be, because not every circuit on its own will have an EMF. In the bigger picture, ultimately, of course, there must be an EMF somewhere, but not necessarily in that circuit we are looking at. So there's no EMF, right? I mean, there's none here, which means that's exactly the point. That's why I say we have to take it basically at face value. Intuition says, well, hey, I should have an EMF, right? Because we know that circuits typically would have one, but there is only an EMF when there is one, in other words, so to speak. Like here, we even have two actually, right? Typically we have one EMF, but it doesn't mean that in any circuit we draw, you always have an EMF. In the bigger picture, ultimately, when we have maybe this is just one box of many, which we combine then somehow, whatever, maybe like that, and this is this specific box, but there are others, then yes, at some point we must have an EMF somewhere. Otherwise, simply nothing will work, right? That's crystal clear. But for the specific EMF in such a situation, that doesn't have to be an F on its own when we just pull in, so to speak, or enlarge, like and go into that specific circuit, into that specific box. So what I want to say is, you may have something like that, and like this, right? And that is the circuit on its own. So then, of course, yes, somewhere there must be an EMF, no? Crystal clear. Otherwise, it won't work. But if you then now only look at this one, that box here is actually this one, then there's in that specific sub-circuit no EMF. No?
Yeah.
Is that okay, Chris?
Yeah.
Mm-hmm. So that means, as strange as it kind of seems, in that specific, and that's a bit the secret of these circuits, you always have to look at what you really look at. If there's no bigger picture, there's no bigger picture. Of course, ultimately there must be one, But in that specific case, there is none. So when you design that sub-circuit, so to speak, then you have to design it as such, of whatever you want to achieve in that specific sub-circuit, for example. There's always a purpose, ultimately, why you have a specific circuit, sub-circuit, or sub-sub-sub-circuit designed like that, because you want to achieve certain results in terms of resistance, voltage, or current, actually. And then there's ways to put them together in order to achieve that specific situation. That's then especially when we talk about, say, control mechanisms or ultimately integrated circuits for computers, right? They're nothing else but circuits, as the name says it. And as it's like that, it's first of all correct what you say. Of course, we know that this one minus this one, because, right? Why do I say minus for the second one, Chris? Why do I give it a minus sign? Or could, of course, be the other way around. It doesn't matter. It's just a question of what you say is plus. But in tendency, as this goes forward, we in tendency take this one as the plus, right? So why is this one having the negative sign?
It's the other direction.
Yeah, right? It's always helpful to make the loop, right? Symbol. Say, okay, so this one goes this way, this one goes that way. So clearly they're opposite. That helps. Just the visualization already helps. So that's one part. Then the second part is to say, okay, this is obviously the sum of the PDFs, even if it's minus, that doesn't matter because it's a simple direction issue. And that is actually 0 because there's no EMF. The sum of the PDFs is obviously must be 0 because there's no EMF, which means in consequence then, of course, that they have to be equal. That's actually the whole secret, so to speak. And henceforth, when we then go into it, in the next steps, then we can prove what we've done before, then we go into this one, right? So then we can, I don't repeat that, we did that last time. Then the next step is this. So this is the first step, so to speak, to say why are they like that? It's not necessary. Usually they're not equal, right? Because it's not 0. So somewhere that EMF must be integrated. For example, this one is equal to this one plus that one. So that means if there would be an EMF of 2 volts, then that would have to be added to whatever is in this circuit. So this one is then including that one and this one, so to speak, or vice versa. That we say this one minus the EMF is equal to this one when we rearrange it, right? So in that case, I just make it briefly in orange. So that could be that we then say I is equal to this one. Let's assume it's now 2 volt different situation. It would be 2 volts plus the I2R2, or we go and say it's I1R1 minus the 2 volts is equal to the I2R2. That would be 2 volts. If there would be an EMF. With an EMF. So obviously the EMF influences the values in the various PDFs, which makes sense as well, of course. But if there's no direct one integrated in that specific circuit, then there is none. And then, of course, they must be equal. So something must be happening. So either everything's equal, so it's a 50-50 split, for example, could be one, this one, this one, this one, this one, it's all 50-50. Or, of course, the values have to be adjusted. It's one of those typical ones, right, where you have to balance them out. So if that one goes up, that does not mean that one has to go up. It could be compensated, for example, with a higher resistance, for example. So if the resistance on this one goes up, then something happens on this side because the total due to the higher resistance goes up. Hence, the total must go up as well. But then it's a question of how we distribute it between resistor and current, for example. So we can have a different resistor here, and then we can influence the current. So if we increase the resistor here as well, of course, the current must go down as a result of the increased resistor here. Or I said, nope, I want to have a different result for whatever reason. So I want to have the current go up, so I have to reduce the resistor. So I will have a smaller resistance here than there. Then I have a higher current through this one for whatever reason, right? That may then be related to the energy I want to use. Maybe that resistor represents a consumer, stuff like that. Huh? So that is then the reasoning behind the rationale why I start to modify certain components in certain ways. But the basic relationship is this one in a parallel circuit. When we have to define and think about what is then the result for the resistance. Huh? So that's the starting point. Okay?
Yeah.
All right, okay. So that was actually the whole the revision part I wanted to do. So now we do a couple of calculations, starting with simple stuff, and say you have two resistors. These are two. This doesn't matter which one, but we say it's 5 ohms. Huh? So each one is 5 ohms. And we have R3, which is 10 ohms. And we connect them in series. So what is the total resistance? Huh?
20.
Yeah, exactly. Huh? Yep, straightforward. That's easy series. That's always extremely important to say, what am I talking about? Am I talking series? Am I talking parallel? Sometimes you have to figure it out in the scheme of a bigger circuit, what is what, but we are coming to that when we deal with more circuits in more detail, actually, exactly. So the RT is, of course, R1 plus R2 plus R3, as it says, straightforward. So, and we have a simple circuit like this. And we just have, okay, we do it like that. Goes here, and you have two consumers. All right. So first of all, in which direction is the current flow increase?
Anti-clockwise.
Anti-clockwise, exactly. And why is that so?
Because it's a positive flow of current.
Mm-hmm.
And the electric cell has plus that goes on top and negative on bottom.
Yeah, exactly. Yeah, good one, exactly. So very simple, kind of. So the bigger one indicates the plus, right, in the simplified version. And then, of course, we have amp meters, voltmeters, especially. So, and we want to know, of course, make it like this. We have voltage 1, of course, here. And, of course, voltage 2. Okay. So, and we have an EMF of 2 volts. So EMF is 2 volts. And the PD, let's say PD1, it doesn't matter which one it is actually, is 1.2 volts. So what is the PD across the second one? So PD2.
It will just be 0.8.
0.8, exactly right. So it's really straightforward. You can just basically it goes, well, it's a bit extremely said, but basically we don't have to think too much even, right? It's just straightforward. Of course, especially you're now already very familiar with them. You can instantly say, well, hey, it's series, so easy. the EMF must be equal to the sum of the PDF, so henceforth, of course, the difference is 0.8. Simple algebra in many cases for these circuits, actually. Now, the next one is quite an interesting one, a bit more interesting. That is just basically revision of what we said once more. If you have 5 cells with 1.5 volt, 5 cells, and how would you connect them if you want to have another 7.5 volt, if you want to achieve 1.5 volt, or if you want to achieve 4.5 volt?
For A, I would connect them in the same like direction.
Yep, which means in terms of you know, you can such questions you can always answer basically like series or parallel, right? So would you for A you had it right? It's in one line, so that is what? Series or parallel?
Oh, a series.
Yeah, exactly right. So that is, you can easily just say series, for example. Okay, all right. So that's straightforward, right? You can easily see, okay, 5 times 1.5, of course, 7.5, no problem. Now, that one is a bit different. B is a bit, well, you can, it's various ways to do it, actually, but what is the most simple way to get 1.5 for the whole circuit?
For 2 pairs would be facing towards each other.
Okay, yeah, all right, okay. And then, so basically that you get the difference from the directional flow, huh?
Yeah.
Okay, all right. So we say the answer is 2 in opposite direction, 2, 3. Huh? So that means there we have 2 times 1.5, let's say, and let's make them the minus. 2 times minus 1.5, 3 times 1.5. Huh? 4.5 minus 3. Okay, and we get 1.5, of course. Huh? Or what would be another way to make this happen, the 1.5?
To have them all connected in parallel.
Yeah, exactly right. That would be really the most straightforward. So you see here, it gives a bit a kind of a practical view of all these theory that you say, oh, okay, hey, if I have 5 cells, in this case now of the same voltage to make it a bit more easy. So it's like the typical small batteries, for example, like a 1.5 cell volt cell. And you have them, so you want to drive something, maybe a torchlight. So of course, in the end, it's a question of the intensity as well, for whatever reason. And in one case, it results that you need 7.5 volt. Okay, I just put them in series. So obviously, I need to have quite some space to put them into series, so to speak. Hence, some reason why torchlights have a certain length, because you put the batteries typically in series in there. Whereas on the other case, if you need only 1.5, you just put them in parallel. Huh? So it would be the typical picture where they are like stacked on top of each other, kind of, so to speak. Huh? And what about the 4.5? It's a bit more tricky.
4 of them is positive and 1 of them is flipped.
Okay. So 4 times 1.5 plus 1 times minus 1.5. Huh? Okay, so 4 same and 1 opposite. Or flipped. Okay. So such questions obviously go a bit more into math than practical physics, so to speak, because you just have to say, okay, how do I achieve with 5 elements a sum of 4.5, right? So obviously there can be different connections then as well. Now, when we link it to physics, we can say, well, I could connect two in parallel, for example. Let's draw it like that. Oops. So we would have two in parallel. So that would be a 1.5er, so to speak, overall. And I could as well then connect them in series to two more in parallel. So I could do it like this. Oops, so then I would have the same effect. Huh? So this is a very classical example, kind of, where you say this is more what we will encounter, right? So this with the opposite direction, of course, you would link them then as such in the design so that they flow in the opposite direction, which means you actually have to come to a parallel loop as well. Otherwise, you will not have the anti, so to speak, but in a different direction. But this one is a very clean case of saying, okay, I have 5 cells and they have to result in 4.5. So, of course, there's one missing, one too many, so to speak, my bad. We only have 5 and not 6, so that could be like this. Huh? Right, so that would be another version of doing it, right?
Yeah.
Why is a different story. Why should we do it as complicated as that? But, well, for whatever reason, it should be a 4.5. Of course, then the other question is then why don't I take one specific 4.5 volt cell? Good question, actually. But maybe it's much cheaper to have the standard 1.5 volt cell. There's many abundance of that. The 4.5 may be more special, already more expensive. Just to say, it's probably not true, but just to say, so the 1.5 volt could be cheaper in the end than the 4.5 volt. Theoretically possible, right? And henceforth, it's then in the end ultimately still cheaper to connect them as such in a series of parallels. You can think of that parallel with just one element. It's a bit a stretch, but think like that. So I have 3 parallel circuits, of which 2, of course, need 2 elements to get the 1.5 still. And of course, then the question is, why would I even need 5 cells if I only need 1.5, right? And have to get 4.5. So why do I not just take the 3 in series, for example, like that? And be done with it? Good question, but that is then really the design of the circuit, why it makes sense to have such a parallel circuit integrated into the overall. That can have many different reasons, actually. And we talk about, of course, EMFs. So it looks a bit like PDFs, but of course it's EMFs here. So I just misused a bit the symbol here, makes it a bit faster. But we talk about EMFs, so strictly speaking, I would have to draw it like an EMF, not like an MPD. Okay, so there's a bit an idea of how we're going to do that. But, you know electric vehicles, Chris, right?
Yeah.
So, have you ever thought about how many batteries are in one electric vehicle?
I don't know.
Yeah, it's fine. Because we just look at, let's say you see a Tesla, for example, that's quite common, especially in Hong Kong. In China, you see many more brands these days anyway, BYD, for example, in Shenzhen. So, okay, they have a battery. That means there's no energy production on board, so to speak. So they need cells, That's why we call them electric vehicles. Is slightly misleading. It's actually electric vehicle with cells, and the cells are actually batteries. So instead of having cells which are producing energy on the spot, that's possible as well. But that's not how the current electric vehicles drive. They're like a toy car, an RC remote controlled car, where you plug in some batteries, then they drive around. It's actually the same thing, but in one-on-one size, so to speak. Huh? So the basic principle is not different to a toy car. You plug in one or many batteries to make it have the energy, the electricity to drive around. The ones with the fuel cell, they're only in the making. Some are existing already, and that will come more and more. But right now, we have like a huge toy car. And of course, the question is now, how many batteries do I have to plug in? And the funny, interesting thing is when you look at the top and say, well, this is my EV car, actually. So there's no one big fat battery. Could be, right? And say, okay, this one produces all the juice we need, and it lasts for a certain time so that we can drive a certain range, a couple of 100 kilometers. The reality is you have thousands of batteries put together, actually. I think, as far as I remember, in the Tesla, there's about 7,500 batteries. So there's a lot of batteries. They're not that big, huh? So they're actually then, of course, it comes the question of parallel and serial, of how do I arrange these batteries. And typically, again, I can't remember that either. You have certain battery packs, maybe 10 batteries, and they're put into one pack. Parallel, serial, depends. We are not going into that here, but just to get within an idea. And then these 10 batteries packs have to be put together as well. So we have 750 battery packs, for example, which have to be arranged in the car in such a way that we get the desired result. So we want to have a certain I, obviously, that's the key driver. We want to have a certain energy coming out of that, but we need to put them in. And that's why one reason we can make the linking it to mechanics. If you look at the car now from the side, just make it a very simple box car, then you have the batteries all around here, something like that. Huh? So that means the center of gravity is very good, very low. If you compare it to, say, a combustion engine, which has a huge engine here, which is about between 350 to 500 kilograms at least. So if you have a high-powered engine, you have in tendency a higher one. So it's very front heavy on top. And it's, of course, center of gravity is different. Whereas the electric vehicles, they may even have, if you look at some of the cars, they have a 4 in the signage on the back of the car, which means actually they have the electromotor here, but straight to the wheel, which is actually pretty cool. You have very short ways, right? They have the momentum from the electric motor go straight to the wheel with no big difference. No, you don't need a long shaft. If you compare it to the now I should have made that in green, actually, not to confuse it with the engine. Whereas if you have the engine here in the car, then you need a transmission, and if you have a 4-wheel drive, even worse. Then you have a transmission very long all the way to the back. Then it goes out to the axles here, and then you drive them. So you can imagine the weight of the so-called drivetrain. They call that a drivetrain typically. The engine and the transmission and the gearbox, of course. That is heavy, heavy, heavy. You know? And it's then still front heavy. Whereas with the electric vehicles, well, you can put the batteries basically to the bottom of the car, kind of. Just make sure that they are very safe and don't explode or getting into fire. Not so good for the passengers. But of course, a tank is somewhere here as well. So it's a certain risk as well. And on the other hand, then, because the engines, meaning the electric motors, are just close to the wheel, they don't need any space. So that's why the electric vehicles have much more loading space than a combustion car. It's a nice side effect. Huh? Just to keep that stuff a bit in mind when we talk about these circuits. Why do we do it in parallel, serial? Why do we make combinations of that? That is, we want to have a certain result, and most obvious, an electric vehicle these days is a very obvious object where we can think of how to arrange these thousands of batteries to provide the necessary output so that we can drive these four wheels and move the car forward. Huh? That is then all driven by that purpose, how we design in the end these battery packs, huh? Make the serial and parallel. Okay. Then just to go into the parallel circuit, nevertheless. So if we have again two resistors, R1 or 2, and they are 10 ohms, huh? And we put them into parallel. So what is the total resistance?
5 ohm.
Okay, that's fast. How did you do that, Chris?
1/10 plus 1/10, and then bracket it to the power of negative.
Okay. Okay. Good. So then you get 2/10, right? Obviously makes it 1/5, and you invert it. Exactly. And then you get R5. Yeah, that was fast. Very good. Okay, so this is the key point, right? Of course, it will become a bit more difficult if you don't have the same values. I mean, one is known, one is not known, so to speak. You may have the total resistance given maybe as well, and you want to know the split, or maybe one is already given, you want to know the second one. So the calculation becomes a bit more difficult for the equation. But other than that, no. So yes, that's quite straightforward. Just have to keep in mind the inversion. So once more, if we can just do that mental math, so to speak. If you have 4 10 ohm resistors, what is the total resistance if they're in parallel?
For
So each four resistors, each has 10 ohms. So what is, and you connect them in parallel again. So what is the total resistance?
3.5.
Exactly, huh? Yeah, good. All right, so we get 4/10, right? So that means 2/5. And then we invert it, huh? Okay, 5/2, and then you get your 2.5, exactly. So this is a bit like mental math, actually. Of course, there will be such questions. It seems seemingly simple. Some struggle already. Always jot down the steps, nevertheless, huh? Okay, this is now a bit too simple. Okay, there we go. That's maybe, and I'll write it down verbally because if it's a drawing, it's comparatively clear. Let's say we have 100 ohms and 200 ohms in series, and we put that in parallel with another one of 200 ohms. Huh? So these two are in series, and then they are put in a parallel circuit with a 200 ohm.
So 1/100 plus 200 and plus 1/200.
Okay, so 1/200. Okay, agree. And this one is how much? I mean, sorry, this one.
Total is 1/300.
Yeah, exactly. Huh? So okay. So how should we solve that?
So it becomes 2/600 plus 3/600.
Okay. Yo, very good. So we see why sometimes certain math we did years ago, where it's sometimes a bit difficult to imagine what are we even use it for. There comes some practical application at the end, right? So to speak, that we figure out, okay, so we have obviously 5/600, And henceforth, what is the total resistance now?
120.
120, exactly. Huh? So it's from the outside, right? You get a total a result you cannot really predict. You really have to go through the calculations. I mean, there's no fast way. Of course, with simple values, yes, there is. Like we did it before. With a bit more complicated ones, no. And it's not obvious, right? I mean, with serial is very obvious, clearly. Whereas here we have to say, okay, I have a 300 one, I have a 200 one, I put them into parallel, and I get a total one of 120. It's not so tangible at first glance, huh? Exactly. So there's no other way than going through the calculations. Okay. Then what I want to cover before we go to the next one, then it's probably a good time after the next section to have a brief break. Now, because there's certain issues I would like to with the parallel there. What is a bit special with parallel? Like you said it, I like what you said. When you combine two or more resistors in parallel, two or more resistors in parallel. Huh? So what happens to the combined? You can say that as a general rule, and you mentioned that before. What can you say about the total resistance as a general rule without knowing the detailed values? In terms of what is the combined resistance? I'm sorry.
It should be a lower resistance than either resistance of the resistors.
Yeah, yeah. Lower than the individual, exactly. Now, in practical terms, what does that mean when you think of the general idea of combining VR and I? Assuming that of course, you have to make a certain assumption. What happens to the current? As a result of that?
It splits.
Okay, but yes, but what? That's fine. That's correct. I'm aiming more at what happens to the current in total when you
it should be higher.
Yeah, exactly. The current, also the current draw will increase, huh? Because there's less resistance, right? It's very simple. So if I look at my basic situation that I put them into parallel, then they draw more, actually, than the individual ones. And that is something which people underestimate, because if you think of a socket, like you have a socket here, let's take the Hong Kong one, something like that. Or maybe you have a combined one where you at least have two outlets, like let's put it like that. Huh? And of course, with their individual switches, typically switch them on, and you plug in two devices, right? One here, all nice. But we have these so-called multipliers as well. So you can at least plug in one, just this kind of socket which allows you to plug in, for example, two now into the same socket. Huh? You know what type I'm talking about, right, Chris?
Yeah.
So you know these bulky squarish things which you can plug in here, has no cable, but it now kind of doubles the sockets, right? Like a duplicator, actually. Sometimes it's called a duplicator as well. So that means, or you can even make it even worse and take one duplicator, put another duplicator into the duplicator, and start to have three. So you can, instead of one, you can suddenly have 3 cables, so to speak, coming out of it, and maybe here 2. So instead of 2, you suddenly have 5.
Yeah.
And why is that maybe not such a good idea?
Then the resistance is, well, it will stack.
What is that kind? What will happen if you start to plug in more than one? So if you plug, let's say when we have these multipliers, so as a result, you plug in 3 plugs here and here 2, because you make a double one, right? Double multiplier. So you have in the end 3 here and 2 here, also 5. What is the connectivity type when you plug in 3 to the same source here with the multiplier? What type is that? Is that serial or parallel?
Parallel.
Exactly. That's very important to remember. Very good answer, because quite a lot say, well, it's kind of serial, and no, because it's split, right? If it would be parallel, you would just put them one after the other. So that's a different story. So a multiplication means clearly parallel. It's kind of in the picture, if you want to say so. The moment you put in a multiplier, you split it, but not everybody's always aware of that. So that means you make parallel circuits. So you have suddenly, in terms of practical picture, so what used to be, let's erase that. So what used to be something like this, right, suddenly becomes something like that. With my multipliers. Sorry, that's wrong. That's not enough. So this one becomes like that. Assuming it's 2, and this one is even worse. Splits into 3, and like that. And of course like this, which was before already as well. So, I mean, so I can eliminate that one, excuse me. So now we have it right. Like this. So what has become, my bad, excuse me. I got a bit, so it's actually, so we have a 2 here, sorry. So, and we have to split into 3 here, so. Okay, so what has become, what was 1 has become 2, and what has been 1 becomes 2. So we certainly have, instead of 2 in series, which is here actually like in series, we could as well, of course, just look at 1. It doesn't matter, right? Just makes it a bit more impressive in the end. Then you have suddenly a serial of 2 parallel circuits. And what happens to the overall circuit, therefore, in terms of the PD or the current, both ways? What is the result of all that, Chris?
The total resistance of the 2 parallels, like the they'll add up.
Okay, but what happens in the individual one? Compared to here, right? I mean,
lower.
Yes, right, exactly. So each one will draw, will have a less. So what was able to potential the PD here has become a fraction of it. Same here, actually, even worse. So there will be much more current be drawn, right? Which is the idea, because of course each one here results now. Assuming this resistor, you can imagine this is like then having plugged into the duplicator another cable. So now you connect one computer here, you connect a printer with this one, you connect another notebook computer maybe here, There's maybe even a small coffee machine for whatever reason, and there's maybe a router plugged into it. So suddenly you have some massive consumers, which was limited before, and as they all draw their own current because they have a certain wattage, right, consuming certain amount of electricity, typically listed as how many watts they consume, which of course results in the current they draw. And suddenly there's a huge kind of surge here towards the supply, which means if you add them up, you have to, and you turn it into amps, you realize, oops, maybe my 10 amp fuse, because behind this one maybe a 10 amp fuse, maybe behind this socket, so to speak, or maybe it's in series with other sockets as well, so they actually, or maybe even parallel, that depends on how the electrician made it. So if there are now two such kind of sockets in the same room, but they are put into parallel, then of course the 10 amp fuse serves 5 amps in this one and another 5 amps in the other one, in theory at least. And if you now start to multiply that stuff, you suddenly have maybe 10 amps on one. And if you repeat the same stuff on the other one, because it's a room where two people are working and they plug in wherever they can, and each one has their own devices, suddenly they start to draw in maybe 20 amps. Huh? Or maybe just with this one alone, already 12 amps. What will happen if it's properly wired, Chris? If I draw too much, if say I draw 12 amps through that 10 amp fuse?
The fuse will blow.
Yeah, exactly right. So that could be a typical question of what happen in terms of what happens if you misuse and start to integrate such kind of parallel circuits. First, you have to realize if you plug in more sockets than there should be with these multipliers, it results in parallels. As a result of that, the resistance goes down. In consequence, the draw goes up, and it may be too much. And hopefully, it's properly wired and the blue fuse blows. So that's why, when using an extension in terms of multiplier, it's best to use one which clearly states for what it's made. So, in other words, instead of doing that homegrown approach I just described, it's better than to take one which maybe has a 3 plugs here, typically the on-off switch, and this one then goes into the socket, right, with the 3 prongs and something like that. And then, and then it says as well the wattage, the amps, and then it's easy to calculate. So it's not nothing to use these extension or multiplier cables, right? They're usually, that's the box of plastic with the plugs, and then there's the cable, maybe 1 or 2 meters long, something like that. So it's really worth to read what is written on the backside and says how many watts, how many amps. Of course, for any volts, but typically it's 220 volts, right? Or it says it's suitable from 110 to 240 volt. That's quite typical as well. So it's okay. They can absorb quite a range of voltage, but the limitation comes in with the amps. And of course, it says then AC/DC eventually. Is it only AC or is it DC as well? Or the other way around. Usually nowadays, they're typically AC/DC, so both type of current actually. That's not to be underestimated actually. If it's only for one, you will have fireworks if you plug it into the other one. It really is not accessible. If you have alternate current, and you plug it into a direct current socket, sparks will fly, guaranteed. So, but typically nowadays it's AC/DC for both, suitable for both, but it has to be stated on the back, the voltage range, 240 volt, and then of course the amps, for example 10 amps, which eventually is reflected in the watts sometimes as well. So that means that when you plug them in, say, well, that you are not suddenly a massive consumer, or 10 amps is not too bad. Typically it would not overload the system when you plug in 3 of them. But if you have a hi-fi stereo at home, which can do like 100 massive sound to the delight of the neighbors, a couple of 100 watts, that may start, and then in parallel you think you connect it with the coffee maker of high-end one with 1500 watts, plus some high-end computer for number crunching, that may blow the system. So it's worthwhile to check what is stated on the back. Huh? So maybe in the end, you have to really make sure you plug it into 3 different sockets. And of course, they're individually fused. Otherwise, it's the same effect as using one of those into the socket. Huh? So it really then depends on how the sockets are wired. For the household, that's okay. Usually that shouldn't become a problem. But of course, if you think of industrial application, it becomes really important that the wiring is then respectively as such as the demand is made for the machines. So not that suddenly all the machines go through the same fuse again, even if you use different sockets. Huh? Is that okay?
Yeah.
All right. Okay. Then I would say let's take a brief break, 2 minutes, Chris, and then we
Yeah.
just continue with the next. Huh?
One.
What is
Oh my god. Bro has to be different.
Chris, is it okay to continue?
Yeah.
All right, okay. So in the meantime, I made a simple circuit, and we would like to discuss a bit certain aspects of it, huh? Certain calculations. The first one is to say we have a battery with an EMF of 10 volt as given, and this one has a negligible internal resistance. Sometimes it's mentioned like what I just said. Huh? We typically assume that anyway, that this one has no internal resistance. Otherwise, we would of course have to include that in the circuit. But to make life a bit easier for us, that's typically, if it's not mentioned, you can assume there's no internal resistance in the battery. But sometimes it's said explicitly. So there's nothing different than to what the typical standard case is anyway, right? If it says no or negligible internal resistance of the battery cell, of the cell. Okay, now we want to know the current in the 20 ohm resistor, just here, huh? To start with. So how do I calculate now the current in that particular resistor or flowing through that resistor?
So I equals V over R.
Okay.
So then it's 10 over 20. No, the current there is 1 over 2.
Okay, yep, 1 over 2 or 0.5. Huh? In that context, you usually would say then the 0.5, the decimal. Huh? So to speak. Yeah, cool. Okay, and why is the V 10 volt? Or why do you say that V is 10 volt?
Because for its own loop, it's the only component with resistance.
Okay, that's one way to say it. Yeah, it's good, right? The other one you can say, well, if the voltage across each has to be the same as the EMF, right? Parallel circuit, right? So from that one we can as well go into this one and connect it like that, huh? All right. Okay. Next one is to say, what is the total current? So maybe I call that the I1. What is the total current? Yeah.
Find the total resistance first.
Okay, can do. Yeah. Okay, let's do this one.
Well, 1 over 20 plus 1 over 40 plus 1 over 50.
Okay.
So it would be 10 over 200 plus 5 plus 4.
Okay, yeah, good one. So we get
219.
okay. So that's something like 10.5, huh? Yeah, roughly, yeah. Yeah, okay. So 10.5 ohms, huh? Okay, so that's the RT, huh? Okay, and now what is the final step? The current in the whole circuit?
10 over 10.5.
Okay, and that would be a bit less than 1, obviously. So something like 0.95, huh? Okay. All right. So when we now, just as another thinking, so when we see, okay, this is 20 ohms and we had 0.5 amps. Huh? So what do you expect for these two subsequent individual currents? Will they be, I mean, it's a pretty obvious question, but nevertheless, are they rather higher than this one or lower?
Current is lower.
Yeah, right. Huh? So I mean, there's a nice relationship then with the ohms, right? So basically, this should be probably half, right? And this should be yeah, the fifth from 20, right? So 2.5 times, so to speak, inverted. So from that point of view, we could actually do as well the calculation, say, hey, if that one is 0.5 amps, then this one is 0.25. 0.5, sorry, 0.25, and then the last one must be 0.2. Right, if you put it in Ainsworth, I get 0.95. Huh? So that would be another way to come up with the answer as well. Because we have calculated the first one, so then you can say, well, if I have calculated that one, then of course I can as well use the result and put it into the logic relationship that the ohm drives directly the amps, so to speak, because the voltage is accordingly given. And henceforth I can just start to add up the respective currents. And they are a direct consequence of the resistance, right?
Yeah.
Because the voltage, as it's a parallel one, must be the same across each, huh? Like we said before. So I have to have 10 volts each because of that EMF, actually. So that would be another way to do it. Or of course, can go to do it similar to what I just said, but we calculate it still with that one. That we still say, okay, this is V over R. So I can calculate it. But this one is, so there's kind of three ways, right? The one you did, which is very good. Or we can do it in a formal way that we calculate the current for each part of the parallel arms and add them up. Or we say, well, as the voltage is the same across, then the amp is the direct result, linear result of the ohms. So if I have now calculated 0.5 amps, henceforth, that one is of course half of that one because of the double the ohms, and this one is then 2.5 times inverted, so that's 20. And hence also 0.2. And henceforth I can just add them up like that. So
Yeah.
bottom line, there's more than one way typically to calculate. So just if you see it one way, stick to it, pull it through, and the result will be okay. Don't start to waver and say, oh, or should I maybe do it like this? Oh, maybe I should do it like that. In a test, you just lose time, right? So to speak. Then just stick to one way, because there's more than one way to do it. Huh? Okay. Then let's go with this one and do some of those questions. And which one is correct? So we really have to work our way through. That's where I usually say 1 mark is not really sufficient reflecting the challenge you face, because you really have to go through it all.
B.
Okay. And why?
Because the first law means the current entering a junction should be equal to the current leaving the junction. So
Okay.
that means no charge is lost.
Yep. Okay. So we have that one, right? The charges. So we have A and B. So we have narrowed it down.
And second law means that sum of EMF in a loop should equal to the sum of PD of the components in the
Yeah, super. Yeah, well said, Chris. Yeah.
means
Genau, exactly. So this is, yeah. I mean, this one, of course, is now a bit obvious when you really look at the wording. Second law is an expression of the conservation of charge, and it says exactly the same as here. So that doesn't need then too much thinking anymore to say once you have narrowed it down. And the key was obviously here to say what is the first law, right? But I like what you said, because it's coming more to the point then afterwards and says, what does it really mean? And it comes with, like you said, with the conjunction of the current, and this one with the PDFs, with the loops, huh? Of EMF and PDF. Okay. Question number 2. maybe we do it step by step. What would you make first to help you a bit?
I think if I want to do it, I would find the current of I2 and I3 first.
Okay. And when you have obviously two cells now, how about making the loop to give you some idea of because obviously you can see from the answer already, right? So even on one side, it's, yep, it will tell you something here, but on the other hand, by having a minus here, so probably you have to pay attention to the flow, huh? So what is the direction of the first one? Also, it's shown here, but nevertheless, it helps to make it.
They should all be plus.
Yeah, they are the way they are made. So that's quite interesting, right? That we look at it, but the way they are arranged. Yeah, exactly right. So it continues, right?
Is that negative?
So would that be okay, like that, if I draw it like this for the loop?
Not really, because on the second I2 maybe would be the other way around, because it has the opposite. Oh wait, never mind.
Yeah, right. It's tempting. I know what you say. No problem. Yeah, right. It's a bit like, oops, how come? But on the other hand, yes, we go from plus to minus, and so that's fine. And then on the other hand, we go from plus to minus. So this one, the split here, and we say it of course goes. Oops, sorry, my bad. So it goes like this, right? Continues like that. So obviously it doesn't matter in this one in terms of going this way, and this one has to go. So what happens here? So is that, I mean, or in other words, when you look at it, what is it with this junction here? I mean, it's just a side question. It's not really the core of the question, but
so I2 and I3 join.
Yeah. So so there must be something happening here, right? I mean, it's not indicated here because if you have this flow, can it flow in this direction? Just to say, because it comes, I3 comes here. So if it's at that junction, can it flow in this direction?
No.
No, exactly. And so it's something we don't see, right? That's what I want to say. So we have to be careful because we may overthink it at the end and say, hey, if I look at that flow, that makes perfect sense. Yes, goes here, goes here, goes here. Well, it cannot go there because wait a minute, that doesn't work. Right? It's from plus to plus, so it must continue here. So that means there must be something like these diodes, right? Which only let it pass in this way. But not in this way. So it has to go on. It cannot go in this direction. So we can say, of course, because so they will join it. Typically, we would rather think if you have it splits maybe, right? That's maybe a intuitive thinking, because we typically think they combine, but we see that already here, right? They don't. One goes here, but here we have a splitting point, obviously. One goes here, one goes there, whereas here we have a joining point from these two. So that one comes this way, and this one comes this way. But we would maybe, if you look at the loop itself, we may think first it goes this way, which it cannot. That's why, But that's like, as I say, it's kind of overthinking it. So we sometimes have to really say, okay, let's focus. And there's maybe something we don't really have there, but it's not important. That's why it's not there. Okay, so coming back once more, Chris, which one is the answer? Or
So if I calculate I2, it's supposed to be it's supposed to be 6/4.
okay, or did you okay 6/4 because
Because it's supplied by the 1.5 and also the 4.5.
okay, and that would be
1.5.
1.5, huh? Okay, yeah. And is that something which is possible according to ABCD?
No.
No, right? I mean, that's sometimes the beauty of the multiple choice questions, that we can cross-check if you really get the right answer. So something is obviously we have to review, huh? Or to revise of what was going on. So what about, let's say, if you look at the junction, what happens at the junction? What is equal to what?
I1 equals I2 plus I3.
Okay, oops, sorry, I was wrong. I1 is I2 plus I3, huh? Okay, all right. Can we calculate, do we want to have I1? Do we know I1?
Huh?
But how do we go on in order to get I2?
Um, I can only think of the way we calculated.
Mm-hmm.
Oh, you mean I2 equals I3 minus I1? Or,
For example, that would be one. Now, if it's helpful or not, we have to see, right? But it at least could be one step eventually, or maybe we don't need that step at all. Just to think about it, right? What the values you have? So you have resistors, right? You have a circuit. What type of circuits do you see, Chris?
the parallel.
Okay, so we see a parallel circuit. And what can we say about the circuits? So when we say it's parallel, what can we say? What is the most straight answer actually for the parallel circuit?
Resistance.
Resistance, yep, is one thing. So what is the resistance of this one? And what is the resistance of this one? And what is the resistance of the total?
So first loop is just 4 ohm, and then the
4
second one.
ohms, right? Okay.
Second one
Okay,
is
yep.
total of 105.
Yep, okay.
Then it
So
should
we
be
have the
9/20.
yep, okay. So we have the total resistance, right? Does that help us?
Because the first loop also has I2 also goes through another electric cell. So
Okay.
we can't use 1.5 for both.
Okay. Then what can you say for I2?
So I2 has it has its loop has PD of 6.
Okay. So how to, okay, yeah. So where do you want to go with that, Chris? Maybe.
Which I don't think we can use the total resistance directly with 1.5 because because of the extra electric cell that I2
Yep.
passes through. Then I think the 2.2 that we calculated might be useless.
Yeah, okay, yeah, it's a good point. Exactly. I mean, it's a bit like it's good to have a bit try and error at this stage, right? Then it gives us for the future. Of course, we don't want to do try and error anymore. So but you have made you made an interesting remark. So what these two, right? So what is when you look at that loop? What is the EMF of that loop?
So I think that we do I2 and I3 individually because finding I1 and total resistance is finding I1 with total resistance not possible.
Okay, yep. Well, it doesn't really help us actually. So that's why if you look at that loop here, of the upper loop, because we want to have I2, right? So for example, I mean, could as well go the other way around. Of course, we could do the same thing here, but maybe this one is easy. So what is the EMF of that loop, Chris?
6.
6, right? So if you now go with Kirchhoff and say, okay, I have 6 volts, and what must be there for the PD over the resistor?
6.
6, right? So you have an EMF of 6, so you must have a PD of 6, right? And when you look at the, well, if that's really helpful or not, we still have to see, right? But on the other hand, we have the ohms. Of that resistor.
4.
So can we even 4, right? We have 4 ohms. So if I look at my relationship, would that help?
Yeah.
Maybe not. So we would say, so in that, what could we say about, we really can, what we cannot say yet is what about, let's say, we have the current here. So that is a bit, what is the current in this loop, right? Or in other words, is this identical I1 and I2?
No, because part of I1 becomes I3.
Exactly, right. So that makes life a bit difficult, right? So you have to be a bit careful with that one. But if I now blend out, what about if I blend out this one?
then I1 and I3 would be equal.
Exactly, right? So could you utilize this one now?
Huh? Yeah.
Because if you look at that loop, right, then you can say, well, this is nothing else but a serial here, which has one EMF of 1.5 volt. And you have and you can cross-check if that should be the case, right? So what happens? So we say if we look at, I call that loop 1, huh? So we would say I1 is I3, huh? Is that, if I look, I make this one loop 1, huh? That would be loop 1. So what can I say? And what can I say about and I have 1.5 EMF. So what happens to the PDFs in that serial circuit?
A total of 1.5.
1.5, huh? So henceforth, when I look at the individual elements, what can I say?
Well, I think we add the resistance together.
Okay. Yep. Okay.
5. So I3 can be found.
I3 would be times 5, huh?
Yeah.
Like that? Okay. All right. So 5 volts. Not 5 volts. 5 ohms, huh? 5 ohms. So in other words, I3, like you said, so I3 would be 0.3 volt. 0.3 amps, excuse me.
0.3.
Okay. So let's see. Huh? So from that loop we can have the I3. Now, how can we now get something where we can easily calculate I2?
If we know I1,
So, mm-hmm.
then I2 equals I1 minus I3.
Okay, can do. But we said I1 is equal to I3, right? Remember?
But if we ignore I2, then if we don't.
Yeah. Okay. I mean, if now we have to do I2, right?
Yeah.
So, how can you get I2?
We also ignore I3.
Okay.
To only have the loop from I1 to I2.
All right. So just this one, huh? Just this one. Oops, sorry, that was wrong. So just this one.
Yeah.
Okay. Let's see. So we do this loop, huh?
Yeah. So then so then it's just 6/4.
Okay. So when you say 6/4, okay, that's how much?
1.5.
1.5, huh? Yup, okay. Now, and then?
So I1 equals I2 plus I3. So just
Yo,
add it together. So
exactly, huh? So, in the end, seemingly simple, yet not so, huh? So it makes 1.8 amps, huh? Exactly. So this was a bit, it's, or let's say, were there difficulties in it, Chris? What made it a bit more confusing?
the extra electric cell.
Yeah, exactly, right. And how did you overcome that?
By calculating only the individual loops.
Yeah, huh? So just to blend out exactly, huh? So that's always a good approach that you say, okay, I just look at that one. So first attempt is I don't have to look at the second cell because that seems to create some troubles. So I just look at that one, then I have a standard situation, which where I can say one statement, make one statement, and I can make another statement, huh? Hence, I have the I3 calculated, and because of that, I get the sum of both. Now the point is to say not to this one is obviously then the one we thought about in between, right? Was then I cannot just say I1 is I3 in total because it's not. So then I look. That's why that is where the fallacy happens eventually a bit from that situation, right? Because in the first loop, I have to conclude it like that. That's how it works. But it does not really hold true in the big picture, actually. So that's why I choose this, or you choose the second one. And then, of course, it's like what you said more or less from the beginning. So we have 6 volts because it's 2 cells. We just add them up. Crystal clear because they are, of course, in series. So we add up. And hence, if we have a 6 volt EMF, which means we have a 6 volt PDF, which means clearly there we go, huh? Because then the PDF, and we have only one resistor, so that resistor, as it's the only one, must have exactly that one. And that's exactly why you came up with the 6/4, which gives us the current. And then it's to say exactly the original one. So maybe I delete that one. Is then to say, well, actually, I have the junction point, which I identified, or you, as I want, when I say I mean us. Then we come up with this one, huh? This is where the starting point was. So the starting point was completely right to say, yep, it must be in this junction that the two together are equal to this one, right? I mean, you can look at it the other way around. Instead of the splitting, we can say, well, even if it's flowing out, but together they must be equal to what came in. So that holds true. So henceforth, I have, and I2 I need. So either I can calculate I2 directly, but that's probably not the case. Then I wouldn't need that equation probably. So then I have to think, okay, if that's the one which helps me, then I have to figure out what is I1 and what is I3 ultimately, right? And that's exactly what we did. And then the question is, okay, now how do I get I1 and how do I get I3? Then more or less it starts to show that, okay, I3, this is in this loop. So you know what? Yep, I look into that loop. Then I get my I3. And then, of course, I go into this loop. Then there's the trick with the 2 cells, which gives to me, of course, then the I1 because it must be identical. And hence I get the solution accordingly, huh? All right, okay, that was a bit a tricky one. So that's why I say 1 point for that calculation. That's more like 3 to 4 marks to my opinion. Huh? All right, so we just have a little bit of time. So we can use that one a bit, I would say. This shouldn't be too wild. It's just, well, a simple repetition of what we already discussed. So what is the W, the current of W?
Just 3.6.
3.6, right? Exactly. Huh? Crystal clear. Okay. What about B?
Should be 1.9.
1.9. Exactly. So 1.9. And what about Y in question C?
2.1.
2.1. And in which direction?
Towards the left.
To the left. Huh? Yeah. Exactly. So, I mean, we are so used quite often that way. So, I mean, you see it, right? It's basically the same picture as this one, just a bit mirror image kind or twisted, rotated, if you want to say so, right? If you rotate it in this angle, then in the end you get exactly the same as you have already here. That's quite often the case with those. There are not so many variations for the questions actually one can do. And what about Z
Should be
in
0.
question D? Must be 0, right? So that could be, for example, an earthing,
Oh.
where you have a grounding, right? Where you say, okay, I have to put a ground wire here for whatever reason, for example. Okay, that was simple. Now let's see in 4. I think that's a bit too simple. Still have time. Yeah, okay, let's rather look at 5A, huh?
0.8.
And we want to, but 2.8, okay? So 0.8, right? Did I hear you right? Right,
Yeah,
0.8,
0.8.
please, huh? 0, okay, exactly, yeah, okay. 0.8. In B, so 2 cells.
2.7.
2.7. And why is that?
Because the sum of the PD is 8.7. So the sum of the EMF should be the same.
Okay, so you said 3.7 then, right?
Yeah, 3.7.
3.7, yeah, that's fine. I mean, exactly, huh? Exactly, yeah, very good, clearly, right? So always, once that basic understanding is there, it becomes really transparent. That you say, yeah, sure, that one must be equal to this one. So I can have as many EMFs I want and that many cell resistors as I want. In the end, that must be equal, actually. Okay, so something similar again, just the other way around. What about X in this case of C?
7.
7, yep. Okay, and now
So X should be 9 and Y also should be 9.
okay, exactly. Huh? No, very good. So it follows the, well, of course, either way you come, doesn't matter. So either you say, well, it's a parallel circuit, hence the voltage must be the same across. Huh? So that's a very nice example, actually. No matter how many resistors you have in it, they have to be in the end equal to the one here, right? So even if you have 3, 4, 5, 6, whatever, the sum of them cannot be more or less than the one single here. And of course, which on the other hand is then determined by the EMF. So that's a bit like black and white, so to speak. Different faces of the same coin, so to speak. Huh? Yeah, that's very good. So that will help a great deal to solve all these questions, actually. Okay, then that's it for today, Chris. Let me just briefly check. We will have one more lesson this year, as far as I remember. Yep, the one on the 29, huh? So, okay, then I can just wish you Merry Christmas and see you next Friday, huh?
Yeah. Merry Christmas.
Thank you. Bye, Chris.
See you. Wait, he told me he would send me practice. Whatever.
That'll be funny.
That'll be funny. Who joined?
It's
The
me,
stone.
Ethan.
Oh my god, hello.
Oh, Ethan. Yeah, Ethan, you wanna play the Minecraft? I resetted the world so we could all play together with a new start.
Yeah, Ethan.
Yeah, Ethan. Join us, Ethan. Chris is not here, so I don't think Chris is not here, so
Yeah,
I
we
think
can start
it's
without
fine.
Chris. I think that's
I
fine.
definitely agree.
Yeah, okay. I reset the
However,
world, Ethan.
I think we should think for Christopher. Because,
But I just said we don't need to wait for Christopher.
Yeah, why do we need to wait for him?
well, because he's very good Minecraft player.
That's
Hmm,
a fair point.
And
that's a fair point. But
But let's
But-
just start now, Ethan.
yeah, come on, let's just start now, Ethan.
I believe it is morally wrong.
But he's even doing the AI voice just like Ethan.
Yeah, see? Yeah, Ethan, come on, join.
It is morally wrong to reset the world that Christopher has been playing on this entire time. Hello?
I think it's morally correct.
I mean, yeah, he's correct, but who cares? Come on. Let's restart together.
I don't see any moral complications here.
Yeah,
Sorry, but
exactly.
Chris just DM'd me that threatened me.
Besides, since when do we have to consider morality? What are we, like...
He just
Good.
DM'd me, and he's
Oh,
gonna
activist.
bomb the entire. He's gonna bomb Japan again if you reset
Again?
the world.
Oh,
You bumped Japan the first time?
Christopher can go bomb Japan. I mean,
Yeah,
it's only too
well, like,
late, you know,
anyway.
right? Right, Lewis? It's too late. We already
It's not like
reset
we
the
need him
world.
to make more anime. I think we could spend the rest of our lives watching One Piece anyways.
Yeah, exactly. Yeah.
There's no reason to keep Japan right now. I think we're good.
Well, he
Yeah,
just
and
DM'd me
besides,
again. He said he's gonna bomb Hong Kong right now.
Hong Kong.
Hong Kong?
This is a small place. Who cares?
Yeah, it's so small though. Hong Kong is a small place. No one really would care.
Why would anyone want to bomb Hong Kong? That sounds like a stupid idea. You don't have
Yeah,
to bomb
exactly.
Hong Kong. You can probably bomb like. Actually, I just realized this joke isn't going to go anywhere.
Yeah. Who cares if you bomb Hong Kong? It's not that big of a threat. If it's an actual threat, just like bomb the moon or like the entire world,
The
you know?
moon?
I'm sorry, bomb the moon.
No one lives on the moon.
The moon is a
Except for
valuable
Christopher.
asset to our
Think about all the
planet.
astronauts.
Yeah, think about all the space people, you know?
They can
What
just
the heck is a space people?
space people. Are there? Is there anyone in space besides the International Space?
Yeah, there's people.
I'm sorry, the national nation is crazy. That goes so
No,
hard.
there's also people called the space people, you see. They're made out of moon cheese. Yeah.
What, do they also want to kill Jesus Christ?
Oh yeah, they hate Jesus.
Ugh.
They have a different religion, you see.
Okay,
They
then let's
believe
pop-
they believe in Sulong, you know, the moon.
Nubian?
No, wait, what's it called? The bunny, the Mid-Autumn Festival.
I'm sorry, do you say... Do you call the moon bunny Zulong?
Is it not called Sulong?
Where do you get Zulong from?
Wait, no. Oh no, Sulong is for One Piece. Never mind. That's
Yeah,
like the
I was gonna say Zulong sounds like an anime character. What do you
Never mind.
what part
That's
of
a-
Zulong sounds like a rabbit? Zulong!
That's a bunny in One Piece that has this transformation called
Zulong
Sulong.
sounds like a Dragon Ball character.
Who's that?
Where do you get Zulong
Is
from?
it the guy that makes the Senzu bean?
No, he's the person who manages a zoo and he expands the zoo to make it longer. It's Zulong.
Oh
Oh
wow.
my god.
Just like Roblox Tycoon.
Yeah.
It's Zulong!
Anyways, yeah, where's Ethan?
What do you mean? Where's Ethan? He's right here.
Oh, where is
Christopher.
yeah, where is Christopher?
I
Yeah,
will
you
go
know,
call him.
EPS.
Go find. Oh.
Good morning.
Oh my god, he
It's
did
me.
go find Christopher, but where did Ethan
Oh,
go?
hello, Christopher.
Where did Ethan go? Where's Ethan?
Yeah, where did Ethan go?
Sadly, after calling
Did
me,
you
he
eat him?
passed away.
Ah, that's unfortunate. Don't worry, he'll
Wait,
get a
what?
robot clothes soon enough.
Yeah,
What?
yeah.